Excellent. Yes, we can see now.
Yes, 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 yes. You can see?
Yes, excellent.
Okay.
Yes, we can see.
Okay, thank you. Thank you. Are you hear me? Yes?
Yes, fine.
Yes. Okay, okay, okay.
Very
Dear
good.
ecologists, for your attention, just a moment. And I cannot full control. I cannot full control, just a moment. I cannot full control. I see. Can you see presentation now?
Yeah, we can see the PowerPoint window. It's not in
Yes, yes.
presentation mode. I don't know what you're trying to share.
You can make full screen from the presentation, and then the control notes, you can down the screens.
Have some problem with presentation. Yes.
The easiest way to do it is to start the presentation and share the whole screen, or start the presentation and share the presentation window. It is again the PowerPoint window.
Yes.
Yeah, if it you could do it from here.
Okay. Just a moment.
I can share it from here, and you can tell me when to turn the slides if you want. Oh, excellent.
No, excellent. I cannot full control on presentation.
Okay, I will share it. Okay.
I cannot go to the next slide.
Okay, I will try to do it. One moment. Okay, so you can start, and I can. Is it okay?
Okay, okay.
Okay, so.
Okay, but I cannot go to the next slide.
I can do it from here.
Okay, okay. Dear ecologists, excuse me, for your attention is present the short summary of the result of research on subject, the accelerate approach for public key cryptography, implementation of the Internet of Things terminal platforms. Yes. Yes. all existing cryptographic public key mechanisms use model exponentation as a basic computational operation. To provide a higher level of protection from third-party interface necessary for real control system, this operation is performed on number of logic bit n much greater than bit length of terminal platforms on which this operation is implemented. Currently, the most application of length of number is 2044 or 4096 bit. And the implementation of late model exponent operation requires respectively about 2 million processor operations. If you use 4096 bit, it will be need about 100 more than 100 million processor operations on 32-bit terminal microcontroller. You can it's clear that reminded a lot time. On the other hand, the control system work on real time. Based on this, the significant count in such the reservoir for the accelerated of modular multiplication operation. Please, next slide. Accordingly, there is a problem of quickly implementing of modular exponential operation. For stationary computer system, including laptop, this problem is solved by using cryptoprocessor. Which implement this operation on the hardware level and make it possible to speed up its executing by two order. This solution is unacceptable for terminal microcontroller that operating on real time. Here we can consider two ways to solve this problem. First consists of that we use the cloud computation, and an alternative way consists of that we finding the way to quickly implement it on software level. And our research belongs to the second direction. The model exponentation is calculated using one of two algorithms. Both of these algorithms are organized in form of n loops. And loops you can see here, each of which process 1 bit is exponent coded. This algorithm is from the lowest bit of exponent code, and in this algorithm is from higher bits of exponent code. It's obviously that both algorithms are strictly sequential and cannot be calculated parallel. According, the main reservoir for speed of them is reducing the time.
We cannot hear you, Professor Markowski. Maybe, and again, a problem in the connection.
Yes, excuse me. Connection, yes. It's obviously that both algorithms are strictly sequentials and cannot be executed parallel. According to the main reserve for speeding them is reducing the time it takes to complete their basic operation multiplication. The analysis of those algorithms for the modular exponent calculating shows that 67% of its operation consists of modular squaring. The operation of modular multiplication consists of calculation the product multi-digit number and performing the reducing modulo. So we can see the two parts of this operation. This operation can be performed separated execution. This is one way. And another way consists of that we can combine it using combining this operation, multiplication and calculation, the modular reduction, by using, for example, Montgomery technique wires. If you use a separated execution of multiplication, in case of fast option, for acceleration of fast from this operation using special algorithm for fast multiplication, such as Karatsuba or Führer methods. The multiplication number is another way, consists of that multiplication. The multiplication number is organized by multiplied of section in which this number are divided. This approach allowed, on the one hand, to effectively use the processor multiplication operation embedded, and on the other hand, this approach allows to eliminate the operation redundancy of the modular square operation by eliminating the double multiplication of symmetric section of number. Thus, the disadvantage of existing technique wires is that they do not allow it combining the eliminating of operation redundancy, which when calculating root with simultaneous performance of multiplication and reducing. Correspondingly, next slide, please. The goals of research is to accelerate implementation of next slide, please. Implementation of public key crypto system on Internet of Things terminal computer platforms by reducing the executing time of most common operation, namely modular squaring. The goal is achieved by development the special technique wires of combining multiplication and reducing when performing the operation of modular squaring. This technology allows to eliminate the operation redundancy of modular squaring operation by eliminating operation on symmetric components. In other hand, proposed technique wise provided for the possibility of acceleration due to the Montgomery group reducing with use of precomputation. The proposed next slide, please. The proposed method of accelerating modular squaring is based on the following representation of square of number. You can see this is the square of number, but we give to attention this similar production of similar bit is equal production. So we can transform this equation to this view. We can transform this equation to this view. And you can see that floating index in this sum show that it's possible to organize the calculation of square in such a way that length of the multiplier will be decreased during the operation progress. Obviously, if the length of number is equal to the processor capacity, so in case that n equal r, the indicated zeroing on the low order bits does not affect the time to calculating of product. But however, in real cryptographic system, n is more greater than r. So reducing the length of the term during the scoring allowed to reduce the number of processor operation by almost half. In other hand, next slide, please. Next slide, please. And other hand, that fact that least significant digit of the result are equal to zero opened up the possibility of effective using the Montgomery group reduction. This allows you to reduce the number of processor operations for modular reduction. On next slide, this slide this slide shows the example of scoring on this is a very simple example, and you can see the illustration of dynamic reducing of length of operation. You can see by using the squaring according to the classic scheme, you can see that length of operation does not change. By on this you can see the example the execution this operation by using two proposal scheme. According to the proposal scheme, you can see that length of operand and number of operation performed are reduced. So this is the idea which is the base of proposed method. Next slide, please. The dynamic reducing of length of operating during the process of multiplication lead to fact that it does not affect to the value of the low bit of the result. So if the reducing of length, the low bits does not depend of a result of multiplication. It's possible to organize a group Montgomery reduction. So combining within reducing and reducing cycle using the recalculation that depended only the modular, and therefore that practically performed only once when the public key change. You can take to your attention that in a real cryptographic system, the modular is part of the public key. Such the pre-calculation are performed only once when public change is changed. This allowed to reduce the number of processor operation for modular reducing. Next slide, please. There is the two basic idea that forms the development method. In this slide, you can see the formal description of the proportion method. If you have any question, I can explain this work, the work of this scheme in detail. The next slide show. The next slide, please. The next slide shows the example of how the method work when performing modular squaring 53, modular 59. So you can see that we execute 6 because so the length of number n equal n. We execute n cycles. And on the example show that the length of operation decreasing. The length of operator is decreasing. So this is decreasing the number of modular operation. This example also show that we use the Montgomery group reduction. Look here. For examples of fourth cycle, we does not execute the calculate the remainder. We does not execute, but we calculate the remainder only one time. On this is the example of Montgomery group reduction, and this operation executed one for this two-time cycle, for 4 and 5 cycles. It's clear that it allowed us to increase the speed. And next slide. You can see the efficiency estimated. The effectiveness of this method, we for estimated, we use the coefficient of accelerated. This coefficient is determined by the ratio of number n0 of processor operation on Montgomery multiplication in traditional technique wise, and the number n of processor operation in the proposed method. It has been shown that acceleration ratio can be presented on such view. You can see where is the hash is the number of bit on group of Montgomery reduction, and you can see that analysis of this formula showed that with the increase in hash, the efficiency of proposed solution is increased. But efficient is limited by 4. So if we increase hash, the coefficient go to the 4. So it's we can see that our method allowed to increase software implementation by 4 times. On the next slide, you can read the main result of executed work. So the experimental research show that real increase of speed consists of between 3 and 4 times. Thank you for your attention, and I await your question.
Thank you, Professor Markowski. Any questions from the audience? Professor Baldis, please.
Yes.
Thank you very much. A very interesting presentation, Professor Markowski, and very useful for cryptographic systems, as we see is on public key cryptography. Yeah?
Yes, this research deal with only public key cryptography, because of you can see that in now public key cryptography start to widely use on Internet of Things, because of the more and modern trend consists of that we use that technique wise of Internet of Things. Namely, we use the internet as means for data transmitted on the wide sphere of control of real object.
So
and
how you make
for this, if we want that that will be will be affected from the attacker, we must use the public key cryptography, namely for data signature on data with the signature. For this, use the public key cryptography, of course, but as you can see, the computer platform of Internet of Things are not so powerful for effectively executed public key cryptography on real time.
So nowadays, devices are for Internet of Things on 32-bit registers.
Yes.
And the number that we want, as we see, to make explanation for, let's say, for RSA is about 4048 bits.
Yes.
And this is, can you make it now in real time? Because Montgomery also is very hard.
No, because of we execute the group Montgomery, so we execute not the goal of our research consists of that we don't use reduction on every cycle. On every cycle, we use the group of we use the reduction on a real system about one time on 8 cycle.
Very nice, very nice. Thank you very much.
Thank you. Any more questions from the audience? Okay, so thank you, Professor Markowski, and let's move to the next